Waves are fundamental mechanisms by which energy is transferred from one place to another without the transfer of matter. This energy transfer occurs in the direction that the wave is traveling, and it happens as the wave moves through a medium or even in a vacuum in the case of electromagnetic waves. The nature of this movement varies depending on the type of wave, with the primary distinction being between transverse and longitudinal waves. In transverse waves, the vibrations or oscillations of the particles in the medium are perpendicular to the direction in which the wave travels. This means that if the wave is moving horizontally, the particles of the medium vibrate up and down or side to side, but not in the direction of the wave's motion. An example of a transverse wave is a light wave or a wave on a string. Imagine holding one end of a rope and flicking it up and down. The wave travels along the length of the rope, but the motion of the rope itself is vertical relative to the horizontal direction of the wave's travel. The key characteristic of transverse waves is this sideways or perpendicular vibration relative to the wave's direction. Longitudinal waves, on the other hand, have vibrations that occur in the same direction as the wave is traveling. In these waves, the particles of the medium move back and forth along the same line as the wave's motion, creating areas of compression and rarefaction. A common example of a longitudinal wave is a sound wave in air. As the sound wave travels, it compresses the air molecules in its path, and these compressions move parallel to the direction of the wave. If you think of a slinky being compressed and then released, the coils of the slinky move back and forth in the same direction that the wave is traveling. This is the defining characteristic of longitudinal waves, the parallel movement of particles relative to the wave's direction. The speed of a wave, which is how fast the wave propagates through a medium, is determined by both its frequency and its wavelength. Frequency refers to the number of wave cycles that pass a particular point per unit of time, typically measured in Hz/Hz, where 1 Hz is equal to 1 cycle per second. Wavelength is the distance between successive crests, for transverse waves, or compressions, for longitudinal waves, of the wave. The relationship between wave speed, frequency, and wavelength is expressed by the equation wave speed equals frequency times wavelength. This equation shows that the speed of a wave is directly proportional to both its frequency and wavelength. For instance, if you increase the frequency of a wave while keeping the wavelength constant, the speed of the wave will also increase. Conversely, for a given wave speed, if the frequency increases, the wavelength must decrease to maintain the same speed, and vice versa. In summary, waves are powerful carriers of energy, moving it through different mediums in a way that is dependent on the wave's type. Transverse waves move energy with vibrations that are perpendicular to the wave's direction, while longitudinal waves transfer energy with vibrations that are parallel to the wave's motion. The speed of these waves is determined by their frequency and wavelength, underlining the interconnectedness of these fundamental properties.